Okay, welcome to the soil mechanics crash course. I'm Millie. I am in my final year of a double degree of civil engineering and a Bachelor of Commerce, majoring in finance. I'm also currently doing my research thesis in geotech engineering, specifically unsaturated soil mechanics. So for this course, you have a really good set of lecture notes from Arman. He is very concise, he's very to the point, and so they're really good to study with. So if you get stuck at any point, I'd suggest just going back to the notes. When studying for the finals and for quizzes, I found the best thing to do was just go through as many questions as possible. There's only a certain amount of way that you can ask most of the questions that he asks. So if you've managed to see everything that you can, you should be fine. And the last thing that I would suggest is go to the labs as much as you can. They're actually really useful and really informative. There is a lab tech there called Faraj who's great. He has his PhD in geotech and he's really lovely. He'll answer any questions. He runs the course year on year, so he has a lot of knowledge about that. So for week 1, you start with phase diagrams and relationships. Pretty much a phase diagram, as you can see in this photo, is just a simple schematic of a sample of soil. So it just shows you how much air, how much water, and how much soil grains are in a specific sample, and that pretty much helps you characterize the soil that you're looking at. There are some basic equations. It's mainly just algebra, so this whole thing is pretty intuitive. It's mainly just volume, mass, and weight equations. So the first one you have is the total volume of the sample. The total volume of the sample is just the volume of air plus the volume of water plus the volume of solids. So yeah, pretty intuitive. The next thing that you have are the volume of voids. So for the volume of voids, it's just the volume of air plus the volume of water. The mass is slightly different, but it's still logical. So the total weight or the total mass of the sample is just the soil plus the water of the sample. The air in the sample doesn't contribute to any mass or weight, however it just takes up space in the voids. When the sample is not fully saturated, hence it doesn't take up volume, as you can see above. No, air does take up volume, it doesn't take up mass or weight. So when we talk about mass or weight of the soil sample in this course, they are always referring to the dry mass of the soil particles. So the soil particles, when they're referred to, are completely dry. They don't have any water around them or absorbed into them. These are the equations that we use. So those first volumetric relationships, the ones that I just mentioned, it's total volume and the volume of voids. And then there's the mass and weight relationships. They're exactly the same, and as always, weight is just gravity times mass, so 9.81 times mass. The more important formulae are the ones on the right side of this page. They're going to be ones that you should probably just rote learn. They're quite intuitive and not too hard to get a handle of, particularly when you start using them. The first one is void ratio, which is the volume of voids over the volume of the solid soil particles. This value shows the proportion of soil that is soil particles and the proportion that isn't. It becomes important later on when you're looking at how much soil can deform, because the part of soil that deforms is the air. So air gets pushed out, and that's how the deformation comes about. And also in this course, it's important to note that soil particles are taken as incompressible. So soil particles cannot change in volume, they're a constant. Water is also taken as incompressible, so it's a constant. So the only thing when you compact or densify your soil that can change is the volume of air in your voids. The next one is porosity. Porosity is a measure of how porous soil is. An important thing to note is porosity is not the same as permeability, so please don't mistake porosity for permeability. Porosity only determines how porous a material is and the ratio of volume of voids to the total volume of the sample. Just because this number is high or low doesn't mean a soil is permeable or not. Permeability requires all the pores, which is porosity, to be connected in a way for either air or water to flow through. So it's not the same, and you can have, for example, a high porosity with having a low permeability if the voids aren't actually connected. The next one that you have is degree of saturation. Degree of saturation is the volume of water over the volume of voids. So it's just a representation of how much of the void space is taken up by water. So soil is known to either be completely unsaturated or saturated. Saturated means that all the void space in the sample, so if you look at this slide, this whole void section is full of water. That means the sample is saturated and would have a degree of saturation of 1. Anything less than that is known as unsaturated soil. So anything from 99.99999% down to 0% of water in the voids is known as unsaturated soil. Most of this course revolves around saturated soil analysis, as it's often seen as the worst case in soil mechanics because it often has the lowest shear strength and the worst engineering properties. And then the last relationship that we look at is water content or moisture content. They're the same thing. They have the notation of a lowercase w. Water content is the weight or mass of the sample that is contributed to by the water. So the easiest way in the lab to calculate water content is weigh a certain sample and then put that sample in an oven at 105 degrees Celsius for 24 hours and then re-weigh the sample. What you get then is the change in weight of the sample will be the evaporated water that has come out, so it'll be the weight of the water, and then the dry sample you get after you weigh it, after it's been in the oven for 24 hours. And then you can find the moisture content or water content, which is just the weight of the water that's come out over the weight of the dry sample. The reason they set the oven at 105 degrees Celsius is because the boiling point of water is 100 degrees Celsius, so they just get just over that in order to make sure all evaporable water can actually be evaporated. Some more complex equations start to come in, and these are very specific to soils. They're not just your general volume and mass equations. The first thing to remember is density, and density is how tightly packed the soil is within a certain space. So the concept becomes more important when you're looking at compaction in week 2. And for phase relationships, unit weight is more commonly used than density. Unit weight is either the weight over the volume. So it's just another representation of how dense your sample is packed. The next thing we have is specific gravity. Specific gravity is a dimensionless parameter, and it's different for every soil. Specific gravity is a measure of the density of the soil in relation to the density of water, where water is used as a reference density. So it's just saying how dense are my soil particles versus how dense is water, or you could relate it to other things, but water is the most commonly used. In this course, specific gravity is usually assumed to be 2.65. So if it's not given in the question, the general assumption is 2.65 for most soils. The equation under specific gravity, the void ratio times saturation equals water content times specific gravity. This is almost like an interim equation that links the basic equations on the last slide to the unit weight equations below. It can be derived by substitution, however, it's better to just do a bunch of questions, and usually you end up remembering it because it's used quite often. And as you can see, if the degree of saturation is 1, then the void ratio is the moisture content times the specific gravity. The total unit weight formula is used often in questions. So total unit weight is specific gravity times the unit weight of water multiplied by 1 plus the moisture content over 1 plus the void ratio. And so this equation, it's better to just remember that one equation, because from that equation you can derive both the unit weight of a dry soil and the unit weight of a saturated soil. The total unit weight is of a soil that is anywhere between completely saturated and completely dry. So as you can see, if the water content is 0, then that 1 plus water content becomes 1, and so the equation is simplified that way. And if it's saturated, you can see from that interim equation that it becomes just void ratio equals water content times specific gravity, so E equals W plus G times GS. And then you can go and sub that into the total unit weight equation, and that's how it will become simplified for the total unit weight of a saturated soil. So that's most of the relationships for phase diagrams and equations. After that, you move on to soil classification. Soil classification is about as fun as it sounds. It's a very easy process to learn, and it's just following multiple steps. You don't really have to do many equations in it. It's either using graphs or using lab results, and so it's quite intuitive. You have 4 main types of soil particles. These are clay, silt, sand, and gravel. These are the fine-grained soil particles. So a fine-grained soil will have grains of size 75 mils or less. For coarse-grained, you move into having things such as cobbles or boulders, and there are 2 different processes for fine-grained classification and coarse-grained classification. As you can see, the smallest particles are clay, and then it's followed by silt and sand and gravel. Most classification systems show clay as a smaller particle size, but for us, we're using the universal soil classification system, and as you can see, they have clay and silt listed as the same grain size, and as a result, they suggest defining the difference between clay and silt by their reaction to water rather than their particle size. So when water is added to clay, clay will exhibit very plastic and cohesive properties. It also has very poor drainage and hardens and cracks when it dries, whereas silt is non-plastic and cohesionless, so when it's wet, and it has fairly good drainage. So pretty much they act differently when they have water added into the soil, and then it means that all their engineering properties and the way they behave when load is applied on top is different. Clay tends to slip, whereas silt has a little bit more of a friction factor between soil particles, so they stay a little bit, they have more resistance to load than clay does. The next thing that you have are your labs. So in this course, you look at soil classification in the lab experiments when you have your lab time. I'll note again that the labs are really important to go to, and they make learning the content and the methods a lot easier. I know this firsthand because when I did soil mechanics, I did it online, and so we only had the lab videos to watch. And then when I started my geotech thesis, I had to perform all of these experiments on my soil that I'm testing, and I found it really hard because I'd only watched the videos and I'd never done it myself before. I had to pretty much go back and relearn these methods again. So it's better to just be in the lab and doing the lab to learn these methods. They're really easy. It's just better to have that sort of connection between theory and practical if you can make it. Yes, as I mentioned before, Faraj is the lab technician who helps in the classes. He's the best person in the whole civil labs. He has a PhD in geotech and he's helped in the labs for years, so he's very knowledgeable about all these processes. He can most likely answer your questions about just general soil mechanics stuff as well. So he's really nice to talk to. He's great. He's always there. Usually he's just around in the background, but if you do see him and need help, just ask him and he's more than happy to help. So when you're looking at coarse-grained soils, and just a reminder, coarse-grained means there's cobbles, boulders, or not necessarily boulders, but there are just bigger particle sizes in them. You put it through a stack of sieves, which catches the amount of soil that at each grain size. So the sieves pretty much, as you can see, go from the largest grid size at the top through to the smallest grid size at the bottom. You pour your sample in at the top and then it gets shaken, usually in a machine. It will vibrate the sample for you. And then what you have to do afterwards is just weigh how much gets stuck at each sieve, and then that's just used as a percentage of the total weight of the sample. And so then you can decide whether your soil is poorly or well graded. A lot of this course though looks at fine-grained soils. They don't specifically say it, but you end up looking at fine-grained soils and their processes in more detail than coarse-grained, which is probably because usually when you go out on site, you're working with fill, which is usually fine-grained soils. So the fine-grained soils have a different process. You don't have to use the sieve stack for fine-grained soils because majority of the soil would fall through that last sieve, and that would generally end up meaning that you have poorly graded soil if you were to plot the results the same way that you plot coarse-grained results. But that's just because it's almost like an invalid test for fine-grained soils. So instead, for fine-grained soils, you look at their shrinkage limit and the liquid limit and the plastic limit. The plastic and liquid limits are the most important for classifying the fine-grained soils. Both the limits are easily found in the lab and you'll be performing the exercises. So for the plastic limit is the moisture content of a soil at which the fine-grained soils can no longer be remolded without cracking. So it's related to the ability of a soil to undergo deformation without cracking. It is the bottom right picture where you make a little, in the lab, you start with your dry soil and you add a little bit of water to it, and what you're trying to do is make like a little worm out of the soil, and you're aiming to get the same diameter as the steel bar, so that's a guideline for you. And then if it cracks and you can't actually mold it into that bar size, you then have to go in and add a little bit more water. It means you're not yet at the plastic limit. If it holds form and you can see little cracks, and then when you pick it up or you move it slightly, it then breaks, that means you're at your plastic limit. And if you then manage to put too much water in, it will be really flexible and it will stick together a lot more, so it will look very smooth, and when you pick it up you could like swing it around and things and it won't actually crack. That's when you've gone over the plastic limit, so that's when you've added too much water. So the idea is to get the amount of water that in your soil to just hold it together when you're rolling into a worm. The other experiment that you do is for the liquid limit, which is the one that's in the top right. The liquid limit is when the soil starts behaving more like a liquid. So it's at this point not likely to be saturated. However, the addition of more water will make it a lot more runny and unable to hold form. So it's a pretty simple method. You have an apparatus that looks like the top right photo. I'm not going to go completely through how you do it, but pretty much the setup is the top right photo. You turn that little lever and it picks the bowl up and then drops the bowl down onto the base, and you count 25 drops, and at that point the two sides of the groove that you've made should be touching. In reality, it's very subjective. Both of these methods can be quite hard to repeat consistently, just because they are very subjective methods. Is it touching? Is it not touching? Was it 25 blows that made it touch? Was it 21? You do repeat these experiments and then plot the graph. This allows you to calculate the liquid limit of your sample. After you do both of these tests, you take the sample that you've been using, and as I said before, you then go and find the moisture content. So you put it in a little can, you weigh it, you put it in the oven for 24 hours, bring it out, weigh it again, and you then have the weight of your water, the weight of your dry sample, and you calculate the water content at which it is. After you find the plastic and the liquid limit, you can calculate the plasticity index. The plasticity index is just the liquid limit minus the plastic limit. You then compare this to the plasticity chart and decide the fine-grained soils classification. So this is the plasticity chart. So along the x-axis is your liquid limit, and along the y-axis is your plasticity index. So you just go along to find liquid limit and then up to find your plasticity index, and then it'll sit somewhere within either above the U line, below the A line, or between, and that shows you what type of soil you have. Then we move on to week 2. So the first thing in week 2 is clay minerals. Clay minerals can seem a little overwhelming to start with because it seems like there's a lot of chemistry that's spoken about. However, the main purpose of learning about clay minerals is just understanding why a soil will behave the way it does, and when there's a large enough amount of clay in the soil. So when clay is about 30% or more, that's when it will start exhibiting the engineering properties of clay. To make it plastic and cohesive. So, clay mineral units are presented as either tetrahedral or octahedral units, which means they either have a mineral surrounded by 4 OH ions or a mineral surrounded by 6 OH ions. So you can see those in the top photo. You don't have to know about how they're put together. You don't really actually go into detail about what minerals they are. You just need to know that it's these two are the base units, and then from these units they stick together and create sheets which are held together by oxygen sharing of the individual units, and the type and number of sheets that are stacked together determine the type of clay that is made. So as you can see in kaolinite, it's a 1-to-1 of the tetrahedral unit sheet and octahedral unit sheet, and then those sheets are then held together by H bonds as well. And as you can see in the other two, there's 3 layers per sheet rather than just 2, and the difference between those two is just how they are, how the sheets themselves are held together. So they have the same, all the clays have the same units, it's just how they're arranged together that determines what type of clay is made. The most common clay that's used in experimental work is kaolinite, and the clay minerals section isn't really assessed in great detail, so I'm only going to give you a brief overview of the main points. It's not a chemistry course, they don't really test your knowledge of the units and the layers and things, it's more just knowing certain things, which is the double diffuse layer. So the double diffuse layer is a layer of water around these sheets of clay minerals. So the clay minerals, after they create their platelets, as you can see in the picture on the left, they have platelets. The most important thing to remember about this is that they are negatively charged around around their surface. So the flat sides of the plates are negatively charged. The ends can be slightly more positively charged, but you'll get to that later. So then the important thing to know is that the negative charge then attracts water molecules to the surface of the clay. and they're held there by hydrogen bonding, and they create what is known as the double diffuse layer of water around each clay particle. The first layer is known as the absorbed layer, as you can see. It's held very closely to the clay surface because of the hydrogen bonding, and clay in a natural setting will always be hydrated. You will very rarely find clay on a site or in nature that doesn't have that absorbed layer of water. It's always found with the absorbed layer around it, and the layer doesn't even at times evaporate in, for example, an oven drying process. Then after the absorbed layer of water, you have the second layer of the double diffuse layer, which is less strongly bonded to the clay particles. There are weaker bonds, but they're not as strong as the hydrogen bonds that occur with the absorbed water. And then this second layer can change slightly between different clay types, but it's not a dramatic change at all. The different types of clay have different specific surface areas of their platelets or sheets. So the specific surface area is pretty much the volume of the clay particle compared to the surface area of the clay particle. So the different surface area and the double diffuse layer of water contribute a lot to the engineering properties of the clay. A larger surface area to volume ratio, such as the montmorillonite, allows the type of clay to absorb a lot more water than a clay with a smaller surface area to volume ratio like the kaolinite. This means that the montmorillonite is in the presence of water, it has a lot more movements and there are bigger volume changes, which is known as swell or heave. And then when it dries out, there are also bigger deformations and larger settlements because it's losing a lot more water compared to a clay like kaolinite, which has a smaller double diffuse layer. The more water that a clay particle can take on, the worse the engineering properties of that soil, and the more the ground under your building or under your structure will move up and down every time the ground gets wet. So for example, if there's a lot of rain, it will expand, and then as it's evaporating out, it will settle again. So it's really not ideal to have that happening under your building. And then the last thing I'm going to talk about is compaction. This is the second topic of week 2, and it's arguably the most important topic in geotech engineering. I might be slightly biased because this is one of my thesis topics and it's something that I'm looking at. However, construction projects can have huge issues and delays if compaction is not done properly. As a geotech engineer, one of the main things that you go do out on site is checking that the construction team have actually compacted the soil well enough for them to start building or putting the final slab on top of. So this is just leading on to why is compaction important. Compaction is the mechanical densification of soil in order to reduce the ability of soil to move or deform once a load such as a building is applied on top of the soil. So improper compaction of the soil below a building site may lead to settlement of the building, which is like the building sinking into the ground pretty much. So the soil underneath the building is becoming denser and it's almost collapsing in on itself. And as a result, the building that's on top is just sinking down into the space that opens up. So most people think that settlement is the biggest issue. However, it's only half the problem. The biggest issue of improper compaction is the differential settlement. So this is when, for example, one corner of your building settles or sinks. Sorry. This is when one corner sinks, but the other doesn't. So for example, in that last picture, you can see if one corner of the house starts sinking, but the rest of it doesn't, it can often affect the functionality of the building that's on top of it, which is a really big issue. So the difference in settlement is what usually causes things like doors to not function or ground slabs to crack and become unstable. It's almost like soil not passing a serviceability requirement. If you've done steels recently, you understand about serviceability. it's not necessarily that the whole building is going to fall down, but it's more just things like doors can't close, which is really inconvenient. There are a few factors that affect compaction of a soil, such as the soil type, water content of the soil, compaction effort, which is how much force is used when compacting the soil, and initial dry density of the soil, which is the initial amount of soil particle that is present in a specified volume. So for compaction, smaller soil particles are better and lead to greater compaction. This is because they can compress down closer to one another, whereas big particles like gravel tend to sit next to each other, and they tend to be too big to actually move past each other in compaction. So generally coarse-grained soils, poorly graded coarse-grained soils are the ones that will be loose and won't densify very well, and the well-graded fine-grained soils are the ones that will compact very easily on site. So the initial dry density is the amount of soil particle within a volume. So if you start with less soil particles in an area, it'll lead to greater compaction as there is more room for the particles to move. However, if you start with a lot of soil particles in the volume, you're already starting at a higher density soil, and hence there will be less ability for them to move and less ability for them to become compact. Again, this is done in the lab experiments. We're just going to go through some important takeaways from the lab experiments and the results graph. The most important concept is that there is an optimum water content in which the maximum compaction occurs. Any more or any less water in the sample will end up reducing the compaction ability of the sample. So as you can see in the graph on the right, from the parabolic shape of the compaction curve, you can see that there's an optimum up the top, and then it sort of slopes off on either side, which is suggesting that it's not as compact and not as able to be compact at those moisture contents. So in that graph, you have moisture content or water content along the bottom, and you have dry unit weight of your soil along the y-axis. An important idea that isn't really specifically mentioned in the lecture notes is that when you're compacting a soil, the first thing that you're expelling from the soil is air. Hence, when you compact the soil, your soil sample actually becomes relatively more wet than when you started compaction, because the air is being pushed out of the void spaces, and this is being taken up by water that's already in the sample. So yeah, it's always the air that's being expelled from your water, from your sample. It's not the water. At lower water contents, the soil is drier, hence there are more friction between the particles. This means that the particles hold stronger next to each other and therefore don't compact as efficiently. When there is optimum water content, the particles are sufficiently lubricated to slide past one another, and so they can be compact quite well, and hence that's why you get the optimum water content. Overcompaction is not necessarily better, so you might be thinking, why don't you just compact until you can't actually move the soil anymore? In itself, it can actually cause more issues with the foundation of the building. Overcompaction often leads to a much higher water content, and this can lead to lower shear strengths in the soil, because there is then so much water in the soil, or in the voids, that it's almost as if the soil particles are then just floating in water. And so shear strength is really bad. You get a lot of failure underneath your buildings with overcompaction as well as with undercompaction. And then the last thing to mention with compaction are the construction site machines and the number of passes. So pretty much on a construction site, like in this photo, someone sits in a machine like that and goes up and down, and they pretty much do that for 8 hours a day. There are specified numbers in the course notes, but realistically, they're all approximations because it depends on the type of roller that you use or the vibrating machinery. So it's highly dependent on the site and the soil that you're working with. So it will change drastically from site to site. It's not set, but there are a few numbers that are in the lecture notes that are good to have just a general basis of where you think it should be. And yeah, that's the first and second week worth of soil mechanics. Good luck.